Have you ever looked around you and wondered what everything is made of? Why does a rock feel different from a sponge, or why does water turn into steam when it gets hot? The secret lies in the tiniest building blocks of the universe called atoms. These atoms came into existence during a mind-blowing event called the Big Bang, which was like the most powerful fireworks show you can imagine. This amazing explosion created the very first atoms, which eventually combined in different ways to make up everything we see and touch today, including you. In this video we will study the basics of structure of the atom, covering the following topics. Charged particles in matter. The structure of an atom, in which we will cover Thomson's model of an atom, Rutherford's model of an atom, Bohr's model of an atom, and then finally we will study in brief about neutrons. Let us get started with charged particles in matter. In the late 19th century, scientists observed that when certain objects were rubbed together, they became electrically charged. For example, when a comb is rubbed against dry hair, it can attract small pieces of paper. This led to the discovery that an atom is divisible and consists of charged particles. Many scientists worked together to find out that atoms have charged particles inside them. In the late 19th century, Thomson found a small particle with a negative charge called an electron. At the same time, Goldstein found some rays with a positive charge, which helped discover another particle called a proton. Protons have the same amount of charge as electrons but with the opposite sign, and they are about 2,000 times heavier than electrons. To gain a better understanding of electrons and neutrons, let's delve into the structure of an atom. Several atomic models have been proposed over the years to explain the arrangement of electrons and protons within an atom. Let's take a look at some of the most significant models. Thomson's model of an atom. In 1897, Thomson suggested the first idea for what an atom might look like. He thought the atom was like a Christmas pudding or a watermelon, with the electrons stuck inside a ball of positive charge, kind of like how raisins are in a pudding or seeds are in a watermelon. Thomson's idea explained that atoms are neutral because the negatively charged electrons were embedded within a positively charged sphere, and their combined charges balanced each other, resulting in a neutral overall charge. But the drawback of Thomson's model was that it couldn't explain other experimental results such as why atoms are stable. The Rutherford model, which emerged after this, disproved the plum pudding atomic structure proposed by Thomson. So let us study Rutherford's model of an atom. Imagine we're in Rutherford's lab in 1911, watching him conduct his famous experiment. He's using a radioactive source to shoot tiny, fast-moving particles called alpha particles at a very thin sheet of gold foil. The gold foil is so thin that it's almost like a see-through curtain, and Rutherford expects the alpha particles to pass right through it without any trouble. It's like throwing a ball through an open window. It should go straight through and not bounce back. But as we watch the experiment, we see something surprising. Most of the alpha particles do pass straight through the gold foil, just as we expected. However, some of the particles seem to be deflected or change their path slightly, and a few even bounce back, as if they have hit a solid wall. This is not what Rutherford expected at all, and it makes him think that there must be something inside the gold atoms that's causing this unexpected behavior. Based on these surprising results, Rutherford comes up with a new model to explain the structure of atoms. He suggests that at the center of each atom, there is a tiny, dense, and positively charged core called the nucleus. This nucleus contains most of the atom's mass and is surrounded by much lighter, negatively charged particles called electrons. The electrons are moving around the nucleus in circular paths, like planets revolving around the sun. This new model, called Rutherford's atomic model, helps explain why some alpha particles were deflected or bounced back during the experiment. When the alpha particles, which are also positively charged, came close to the positively charged nucleus, they experienced a repulsive force, causing them to change their path or even rebound. However, Rutherford's model also has some limitations. It doesn't explain why the electrons, which are moving in circular orbits, don't lose energy and spiral into the nucleus, causing the atom to collapse. This issue was later addressed by scientist Niels Bohr, who further refined our understanding of atomic structure. So here comes Bohr's model of an atom. Niels Bohr in 1913 proposed a new model of the atom to overcome the objections raised against Rutherford's model, which failed to explain the stability of atoms and the discrete nature of atomic spectra. Bohr's model is based on the following postulates. First, electrons in an atom revolve around the nucleus in certain special orbits, known as discrete orbits, without radiating energy. These orbits correspond to definite energy levels and are also called shells or energy levels, represented by the letters K, L, M, N, or the numbers n is equal to 1, 2, 3, 4. Now, according to the second postulate, while revolving in these discrete orbits, electrons do not lose energy in the form of radiation, thus ensuring the stability of the atom. Bohr's model successfully explained the stability of atoms, validating the idea that electrons occupy discrete orbits with specific energy levels. However, Bohr's model has its limitations, about which you can learn in higher classes. But still, Bohr's model was a significant milestone in the understanding of atomic structure and laid the foundation for future developments in atomic theory. Finally, let us discuss neutrons. In 1932, a scientist named J. Chadwick discovered a new tiny particle called the neutron. It is a part of the nucleus, the center of an atom. The neutron is special because it has no charge, meaning it's not positive or negative. Its mass is almost the same as a proton, another particle in the nucleus. All atoms have neutrons in their nucleus, except for hydrogen. The mass of an atom is determined by adding up the masses of the protons and neutrons in its nucleus. This discovery helped scientists better understand the structure of atoms and how they interact with each other. In conclusion, the study of charged particles in matter has led to a deeper understanding of atomic structure, with scientists like Thomson, Rutherford, Bohr, and Chadwick contributing to significant models. As we explored the structure of atoms through these models, we gained insight into the roles and properties of electrons, protons, and neutrons. Their groundbreaking work has paved the way for further advancements in atomic theory and has shaped our understanding of the building blocks of the universe. Now that you have understood the basics of structure of the atom, open the EduRev app where you get video lectures, chapter notes, and MCQ tests for this chapter. EduRev also provides you amazing courses for maths, social studies, English, Hindi, and many more.